got a few.
I don't mean to do a very formal introduction anyway, but thanks everybody for get closer to the camera.
Yeah.
Thanks everybody for joining, and I'm excited to hear from Nguyen. Is that how you pronounce your last name?
Yes.
Nguyen.
Yes.
From a student from MIT, about generating halo merger trees.
All right. Hi, everyone. So I'm Tree. I'm from the MIT Capital Institute, as well as the I5 AI Institute at MIT. I'm a graduate student. Today, I will talk to you on one of my past and ongoing work on generating halo merger trees using deep generative models. And this work was one of the projects that I'm collaborating with the Center for Computational Astrophysics. So just oh, something happened. It doesn't work. It doesn't work. Oh, sorry.
There.
Okay. All right, so I actually have a few slides of just introduce myself and what do I do for my scientific goal. So I'm interested in understanding the nature of dark matter as well as the implication of dark matter for galactic dynamics and galaxy formations. And I do so by developing a statistical inference technique to infer the properties of dark matter using galaxy dynamics, as well as developing theoretical models of galaxy formation. And I do so by using machine learning, cosmological simulations, as well as synthetic astrophysical surveys. So in the next coming year, what I'm interested in finding is solving is that we're going to have a lot of data for many observatories, including the Vera Rubin Observatory, SST, Romans Telescope, and we're going to have so much data that we cannot possibly process with traditional technique. At the same time, the data complexity also increased. For example, with the Gaia-based observatories, you have a 6-dimensional phase space of millions of stars in the Milky Way, which we do not have decades ago. But at the same time, our simulations and our analysis tool also getting more and more advanced. For example, we have better cosmological simulations that we have better computer that can run the simulation much faster, as well as we have the emergence of machine learning techniques, which can process a large amount of high-dimensional, nonlinear complex data in a very efficient way. So my goal is to connect this observation and theory to both inverse modeling and forward modeling. So what I do can usually be divided in two. With inverse modeling, I do a lot of dark matter modelings in dwarf galaxies using simulation-based inference. But with the forward modelings, going from theory and observations, I'm trying to model the dark matter, like the dark matter halos of simulations using generative model, trying to emulate them. And this is the project that I will talk about today. So let's get started. So with JWST coming online, we have many beautiful images of galaxies, but at the same time, we also have some problems. And this problem is, for example, is the cumulative number of galaxies that observe at very high redshift. We see more galaxies than we predicted from theory. So this curve with the shape kind of show you what the JWST observation is with the count on the y-axis and the redshift on the x-axis. And each of these lines are different kind of theoretical theory, including, for example, the dashed line being semi-analytic models, the solid line being like hydrodynamic simulations. So you see that like overall, we kind of like under-predicted the number of galaxies at very high redshift from JWST. And this highlight the need to understand both observations and theory to have both a strong theoretical framework as well as understanding what the observation systematics there is. And my goal is to tackle the theory side. So in galaxy formation modeling, a very typical way that you can do it outside of hydro simulations is, let's say you have a dark matter merger trees, which kind of capture the hierarchical relationship between each of the halos. And you can add these dark matter merger trees, combine them with some kind of semi-analytical models, which have like scaling relation on galaxy formation models, like gas cooling, star formation, any kind of feedback. And semi-analytical models, there are many of them that I can kind of list here, both traditional one as well as more ML machine learning one, and on different scale from HEN to satellite population of the Milky Way. Combining dark matter merger trees and semi-analytic models, you can have galaxy merger trees. And the advantage of doing this rather than running hydro simulations is that dark matter only merger trees, you only have to run a dark matter only simulations, which is typically much more computational efficient than running a hydro simulations, as well as you have the tunable parameters in the semi-analytical models that can possibly infer you what kind of physical process there is going on in the background. So before I go into this, what I'm interested in is to better modeling the dark matter halo merger trees. And if you haven't looked at merger trees before, this is like an anatomy of a merger trees. This is an example merger trees from, I think, one of the millennium of very small multi-dot simulations, which each of these dots being one of dark matter halos, with time going from the early universe to the late universe, with redshift equal to 0 being here. So this is the root halos, or for example, this is kind of like the Milky Way of these merger trees as equal to 0. And each of the link here showing you the descendant progenitor relationship. So like which halos merging into which halo and which halo evolving into which halos. And the red branch here is called the mass assembly history, also known as the primary progenitor branch, which is one of the most important branch because it's keeping track of the most massive halo over time. And this has the most significant effect in the merger history of this root halo is equal to 0. So for the first part of the talk, I will tell you about the effort that's going on with our team to try to model this mass assembly history better, and then I'll go over a little bit on ongoing progress about generating the full entire merger trees. So to generate a dark matter merger trees, what are the two typical ways that you can do it? So the first way that you can do it is you can run an ML dark matter only simulations, and then you can do some kind of halo finders like rock stars or subfind friends of friends to kind of identify each of these halos of halos and kind of connect them together using some kind of tree construction algorithm like consistent tree, sublink, and our halo tree. And alternatively, another way that you can do it is to generate them analytically using the extended pressure formalism, which kind of model the conditional mass function of given some. So basically, given the mass of the progenitor, given the mass of the descendants, as well as the redshift. You can combine this extended pressure, this EPS technique with like Monte Carlo technique, and assuming some Markov chain properties, you can generate the entire merger trees. But generating merger trees is also very difficult because n-body simulations, they are typically very accurate, but they're also limited by resolutions, which lead to something called the mass volume tension, meaning that if you want to capture massive halos, you want a bigger volume simulations because those massive halos are more rare. But at the same time, for small scale physics, you want higher resolution, and you cannot have high resolution and large volume at the same time because the computational time will scale up way too fast. An example of this is that if you want to model seed black holes with population 3 stars, you need small scale physics, but with direct collapse black holes, you need to be able to capture, say, 10 to the 14, 10 to 15 halos. On the other hand, with extended redshifts, you don't have resolution. You can capture a wider dynamic range, but it's also more accurate because the conditional mass function only depends on the mass and the redshift, meaning that it cannot capture important clustering statistics such as the halo assembly bias. And an example of this is, so I'm showing here is an example of extended redshift mass assembly history compared to n-body simulations, with the y-axis being the mass, the normalized mass, normalized by the root mass, and the x-axis being the redshift. And the top panel just showing the evolution of this mass, while the bottom panel show the comparison. between the extended redshift trees as well and the simulations. And these are three different techniques. And as you can see, that they cannot really capture perfectly the mass assembly history. And this is on log scale, so if you look at this and you try to extract statistics such as the formation time of the halo, the time that the halo formed 50% of the mass, you will actually get a pretty big discrepancy. And this is for three different techniques, using three different separate assumptions, with the Parkinson et al. Being the latest one, still kind of over predicting the mass. And the histogram here is showing you the panel, like an example of like a redshift slice as equal to 0, showing you how much how much the mass is different. All right, so my goal is to try to use machine learning to solve this problem. So first, you always have to ask, can machine learning actually solve this problem? So as a first step, we want to generate only the main frame, so only the mass assembly history of the merger trees. So there's two problems I'm trying to solve. Modeling the entire population of merger trees, because merger trees are inherently random. If I give you a halo with a similar mass, similar dark matter concentration and properties with the Milky Way at different locations of the universe, it might not have the same merger history. So you want to be able to not just capture a point estimate of the mass assembly history, but the entire population. So using generative models is a way to go, because these models are designed to capture the entire population from the training simulations. And the other thing that I want to build into my framework is to see if I can encode the progenitor descendant relationship. I can encode the entire history of the halos with any kind of properties that I want from the halos into this framework. And to do this, to capture any kind of relation as a function, of time, we kind of resort to using recurrent neural network, which is designed to work with time series data like the mass assembly history. So in the ongoing work, we can use graph generative models, some kind of auto-regressive approach, as I will show in the later part of my talk, to capture the entire trees instead of just the mass assembly history. So we arrive at FLORAH, which stands for flow-based recurrent neural network for assembly histories. So let's say that you have an initial halos with some kind of properties. Here we're using the mass and the dark matter concentration, and you want to predict the properties of some kind of progenitor halos. So this is at one time step. You can feed this mass and dark matter concentration into some kind of recurrent neural network as well as time, which is captured either by some kind of redshift metrics or some kind of scale factors, but any kind of time will do. So combining the mass and the dark matter concentration, you feed it into the recurrent neural network. Recurrent neural network gives us some kind of learned representations. So what's notable about this is that if you have some kind of recurrent neural network, it's also have a hidden state. And the hidden state is designed to be able to remember all the previous input, meaning that if it started from 0 to 0, you can remember the entire mass, dark matter concentration, and scale factors from 0 to 0 to the redshift that you're interested in. With this learned representation, so now our goal is that we want to be able to capture the entire distribution of mass and the entire distribution of progenitor concentration at the next time step. To do so, we use normalizing flows. Normalizing flows is a class of generative models that transform this base standard Gaussian distribution via some kind of nonlinear invertible transformations to convert into a target distribution that you want. And here we choose the target distribution to be the accreted mass, which is just the mass difference between the initial halo and the progenitor halos and the progenitor concentration. And during training, the quantity that we minimize is actually directly the log probabilities. So that's basically the likelihood of this, because the normalizing flow gives you a way to evaluate the likelihood directly. And during generating data, we can just sample from this distribution, get some kind of output features. Here's the accreted mass, progenitor concentration, and then convert them into the mass and dark matter concentration of the progenitor halos. And you can do this for multiple time steps. So this is only for one time step. But you can imagine that go from 0 to 0, you can recurrently feed this halo into this recurring normalizing flow framework and end up with a halo at each of the time step. And you can keep on sample until you reach a redshift limit or a resolution limit or mass resolution limit of the simulations.
Sorry, Tree, and maybe I'm not catching up. I'm
Yes.
just want to make sure I understand. So the first step is to go from the mass and the dark matter concentration that you have from the theory, or
From the simulation. So we train this on the simulations.
and then
Yeah.
from that you get what is the learn representation?
The learn representation is basically just a kind of like a summary features of like the entire range from 0 to 0 up to the time step.
But you choose those, right? You train it knowing which are the features you want to extract, or you're learning the features you're extracting.
So we let the network, so because the mass and dark matter concentration go into the RNN layers, the network kind of like determine what like is the important summary statistic that it should use for this learn representations. So basically in a way that you let the data guide your summary features.
Okay,
Yeah.
like an autoencoders. And then you do the normalizing flow from that representation
Yes.
to get.
Yeah,
Okay,
so the normalizing flow convert the standard Gaussian to this distribution.
Yeah.
And if you condition this transformation on the learn representation, then you basically condition it on the previous time step. Yeah.
thanks.
And also in addition, we use the mass and the dark matter concentration. So the mass is kind of very obvious that we need it. For the dark matter concentration, we use it because there has been study to show that the concentrations related to the mass assembly history is kind of like one of the defining factors. All right, so from this framework, one thing I wanna.
Can I ask one more thing?
Yeah.
So you kind of have 3 steps here. Is that for pedagogical purposes? Or
Mhm.
do you train all of this together at once? Or do you like learn the representation ZI first and then learn the next thing?
Oh, yes, I train everything all at
It's
once.
all trained at once. Okay,
Yes.
good. Thanks.
Yes.
Sorry, to clarify that, so the output of your model is given payload mass at a given time for a complete series of the field.
So.
Well, the regenerative payload mass.
So the output of this RNN normalizing flow setup is given a mass and dark matter concentration at, let's say, 0 to 0, it's giving you the mass and dark matter concentration at 0 to 1. Let's say that. And then from 0 to 1, you can go to 0 to 2. From 0 to 2, you can just keep going.
So the redshift is fixed. Cannot like generate payload mass like any generation.
So in a sense, yes. So the redshift of the simulation is fixed because of the way the snapshot is stored. But what you can do is you can take all, the entire, list of snapshots, you can subsample them. So in a way that, let's say the first tree, I have it as 0 to 0, and then the next step is 0 to 1, but the second tree, it could go from 0 to 0 to 0.5. Now, the 0 to 0.5, the 1 is fixed by the snapshot, but you can like vary them as you will, right? Like the delta snapshot doesn't have to stay the same between the trees, and that helps make the models a little bit more flexible.
So the redshift is not the conditioning that goes input to the model, right?
The redshift also go to the recurrent neural network.
So the recurrent network takes the scale factor as input.
Yeah. Yes, yes, and because of the way that you subsample the redshift, you give it some like flexibilities for it to be able to like kind of like interpolate between the redshift and not just like, oh,
This one can generate the payload assembly history on a higher time cadence.
on
Your training simulations only have like 5 snapshots, but the output can have like some routed time cadence for the
yes, because the way that you do it helps us kind of like approximate some kind of like smoother function. Yeah. Yeah. All right, so before we go into the results, one thing that I want to briefly touch over is the simulations that we have. So we actually have 2 simulations which train it on. So one is the very small multi-dark plan simulation. which I would call the low redshift simulation. And the second one is the graph with several gadgets that's ultra high redshift with AstroAI timestamp. So this graph simulation that run by Aaron Nguyen from NASA Goddard to Space Telescope. And the special thing about graph is that, so graph is high redshift, it's running from 0 to 40 to 0 to 6. But the special thing about it is that they're actually 4 graph blocks, each with different volume, with increasingly large volume, but with lower resolution to increase the volume. And the purpose of this is to be able to try to what we're trying to do with graph is we're trying to find a way to combine all these blocks, and that will help you to kind of get over this mass volume tension by kind of having both high resolution and large box size at the same time. And we're using graph and very small multi-dark because if you look at the math assembly history here, and this is an unnormalized version, as the redshift going from right to left, but this is early universe, this late universe, you can see that they kind of overlap at a certain point. So this is where graph ends, z equals 6, but the simulation does overlap. And this overlapping actually help you to be able to combine both very small multi-dark and graph together to be able to create a trees that can span from z equal to 0 to z equal to 20 with sufficient resolution. And it will show a result on that. So this is one of the results, one of the example of a few trees that get generated by the FLORAH framework. There's a few things I want to note here. Once I will leave you to kind of guess which one is the generated trees and which one is the not generated trees. But the thing I want to note here is that for this one, I only trained the neural network from 0 to 0 to 0 to 10, meaning that everything from 0 to 10 to 0 to 15, which is the shaded region, which might be a little bit hard to see on Zoom and it's here as well, is extrapolation. Everything from 0 to 10 to 0 to 15 extrapolation. And I will show you some kind of summary statistic that's showing that this neural network has some capabilities of extrapolating. But if you haven't really figured it out, this is the one that's generated by FLORAH, and this is the one that I've taken directly from the simulation. And this is for the very small multi-dark simulations. So if you take this curve, so this is for the 12 to 13 mass band, but if you take each of these curves, you compute the median and you compute the width of this curve at each of these redshift, you can kind of have your population statistic, and this is what we're going to show next. So this is for 3 different mass band, with the top panel being the same, with the bottom panel being just the residual between the simulation and the trees that emulated by FLORAH, with the line here being the resolution limit. As a reminder, from 0 to 10 to 0 to 15 is completely extrapolation. And here we're showing the median, the 1 sigma width and the 2 sigma width. And you can see that for all of these, mapping over the entire redshift range, we can capture the math assembly history pretty accurately. This bit is a little bit more noisier than usual, as you can kind of see here, because the simulation only have 300 trees, and I've only generated 300 trees here, so that would match the statistic of the simulations. All right, so another thing you can do is you can take this mass assembly history that you just generated, and you can start going from dark matter halos to galaxies mass assembly history. And what we do is we take this mass assembly history, we put it to the Santa Cruz SAM framework to simulate the galaxy stellar mass at each of the redshift. So here I'm plotting as equal to 0, the virial mass, dark matter mass versus the stellar mass. And with each of these are data points, and the band just being the median and the 1 sigma, and you can see that they line up very well. Another thing you can do is you can try to test for assembly bias in this. So the red figures showing you on x-axis the concentration, and this is the residual of the stellar to halo mass function for each of these dark matter mass value. And you can see there's a trend here for both the simulations, and FLORAH lines up also very, very nicely. And this trend here showing you, what it's showing you is showing you a dependency of a stellar mass or something that's not other than the dark matter halo mass, which is usually referring to as galaxy assembly bias. And to go a bit further, if you take all this mass and you compute the galaxy power spectrum from it, so on this right here, just the power spectrum, you can see that they also line up very nicely as well with this the power spectrum, and this is just the residual of the power spectrum from simulations subtract from FLORAH. And you can divide them into two classes, a late forming halos and an early forming halos. And you can see that this is also get captured really accurately. So this also showed you that like some clustering properties that that is dependent on the time of formation of the halo, which is also like an indicator of galaxy has assembly bias. All right. So one thing that we're interested in is to simulate very, very high mass assembly history from 0 to 0 to very high redshift. So one thing you can do is, given the two simulations that we have, you can train one neural network on very small multi-dark and one neural network on the graph simulations or the combined graph simulations, and you can try to concatenate their merger trees or their mass assembly history. So here, what I'm showing here is just the mass assembly history over the redshift, and this is simulation only. But what I can do is now I have a sneakily replace all the line of the simulations by like a trees that generated from 0 to 0 to 0 like 20, which the very small multi-dark network generates something from 0 to 0 6, and then the graph FLORAH, the graph neural network pick it up from there from 0 6 to 0 24. And as you can see that you can using this to generate something that from 0 to 0 to 0 20, basically effectively is concatenate the simulation in a very natural way. So for the later part of my talk, and this is going to be much shorter, I want to present some ongoing work on actually generating the entire merger trees. So mergers are a key driver of process like star formation and black hole growth, black hole seeding, but they're not really captured by FLORAH. And as a reminder, this is an example of a merger trees. And what FLORAH is being capturing is this red branch here with the mass assembly history. But a merger tree is much, much more complicated than this. As you can just see, it's just from the number of data points, but the like complexity, the merger relation, the standard progenitor relationship in this tree is extremely complicated. So how do you capture something like this? And actually, merger trees are also very special graph, right? Like it has a very special structure. There's no loop in this tree, for example, which make technique like graph generative models, like even the diffusion models that you can use for graph generative models. It's complicated all of this. But what you can do with a graph is now you can exploit the properties of this tree here and create a graph generative model that's specifically for dark matter merger trees. So let's say that you pick a halo, you have the entire history of the halo, basically down to 0 to 0. And the halo has some kind of progenitors with some kind of properties. Here I'll just put it at M1 to Mn. So this halo have the history here and some kind of progenitor properties which you can model as a set. And the way that you can separate this problem is you can separate this equation into predicting the number of progenitors as well as predicting the properties of those progenitors. And the first problem you can solve by simple classification scheme. And the second problem you can solve by using regression. But what's actually complicated is that this number can vary. So you need some kind of architecture that's flexible enough to handle this data. And let's say that you have an example merger trees right here. And let's say that you pick this halo to be the halo of interest. And the entire history of the halos is going from 0 to 0 to here. And this halo has two progenitors with some kind of properties 1 and 2. So to model the entire thing, what you can do, so you can write the equations that I just showed in the previous slide, just like that. And you can model. So once you need to capture the entire history, and you can do so by either using some kind of recurrent neural network, some kind of summary, some kind of network that can summarize the entire mergers. So basically n number of variables, right? Because if you change the redshift, the history will also change. The kind of input that you're looking at will change. So you can either use a recurrent neural network, or you can go a little bit beyond and you transform an encoder. And with the transform architectures, you extract some kind of features. With these features, you can just put it to an NLP classifier to kind of like model the number of progenitors here. So in a sense, you kind of models this distribution as a conditioned, Bernoulli distribution. And to predict the properties of a halo, so you can use a normalizing flow if you want, but the issue with using normalizing flow for this kind of stuff is that if I have 3 progenitors, then certainly the dimension of the normalizing flow will change, and normalizing flow can't handle that kind of change in dimension. So what we kind of do is we kind of combine the recurrent neural network with normalizing flow again, where let's say that you have some kind of like seed halo, and the properties of the first progenitor. We feed into some kind of ORN, extract some kind of features, and we use this to condition, the same normalizing flow again. So this normalizing flow is only predicting the properties of one halo at a time and not multiple halos at a time. And you can end up with 1 and 2. And the reason we use this kind of recurrent neural network is because we want to kind of impose some kind of restriction to the properties between the properties of halo 1 and halo 2, because they are not, even though they're not causally related, they are very correlated. For example, the mass of the halo 2 can, by definition, can never be larger than the mass of halo 1. And they all kind of have to sum into the mass of the descendant. So you can use the kind of framework to generate the entire merger trees at each of these steps. So the way that you would do it in generation is you can kind of like go from 0 to 0, and you kind of generate everything with one snapshot at a time. So here, for example, you would generate this entire snapshot, and then you just go from there and generate this entire snapshot. And here are a few examples of just like FLORAH tree, just the structure of the trees, and no numbers here. This is using the graph simulations. This is the real trees, quote unquote real from the simulation, and all here are all different realization of the trees. So the only thing that these trees are sharing is the halo mass and the dark matter concentration at equal to 0. As you can see, like this kind of framework can generate an arbitrary complex structure, as well as very, very simple structure, because, for example, if you pick a halo with a very low mass, there's a very low chance that the halo will actually split. And here you can see that we can also capture that as well. And you can do some kind of comparison that's very similar to how you compare the mass assembly history. By first, you can look at the mass assembly history, and you can try to see if the FLORAH tree is matching with very small multi-dark, so here, so you see that the alignment is no longer perfect, but this is still kind of still work in progress. As a reminder, this is mass as a function of redshift. But what you can do, that the previous framework that can't really capture, is the so-called merger rate. So on the y-axis, I'm showing here is the merger rate, which is the number of count as a normalized by the volume, normalized by the root mass, and normalized by the redshift and the mass ratio. So this is the measure that typically used in galaxy formation modeling. And each of these lines is just showing different descending mass. And let's say, for example, the way that you can understand is if you look at one line and you see that there's a decrease in relation as a function of the mass ratio between the progenitor halos and the most massive progenitor, this basically telling you that the more massive the merger is, the higher the mass ratio is, the rarer the event is. So for example, like having a progenitor with like 100 of the mass of the most massive progenitors will be like much more common than having like 2 halos with the same mass, like Milky Way and Andromeda merging together. And it is shown for different progenitor and descendant redshift slides. And each of these lines, like I say, is the different descent in mass. And with this is the simulation, and the dashed line being the merger trees generated by FLORAH. And you can also kind of like see here that the relation that FLORAH can be able to like have some kind of extrapolation capabilities to extrapolate this merger count as well. Yeah, and I think I'm done here, so I'll leave you with the conclusion slide. But in short, we use recurrent neural network and normalizing flow to get some kind of emulator for the mass assembly history of dark matter halos. And we show that we can combine which we can move forward important statistics like mass assembly history, assembly galaxy assembly bias, as well as you can combine multiple simulations, including things like multi-tier simulations like graph, to create a mass assembly history that ranges from 0 to 20. And with the ongoing work, we aim to extend this framework from just mass assembly history to generate the entire merger trees. And thank you, and I'll take any question.
Are there any more questions? Yeah, go ahead.
That was really interesting talk, thank you. I was wondering, when you were showing the multiple different realizations of the full merger tree, right? They were quite different. They look very different. And imagine, depending on how exactly a semi-analytic model would model the effect on star formation for mergers, etc., could end up with quite different galaxy properties at the end of that.
Yes.
I was kind of wondering, have you started looking at that yet, or and is there a way? Can you kind of does that just effectively just increase the scatter in what you're the stellar mass, for example, that you're getting out of it at the end, or?
Yeah, so like different these mergers. So for the stellar mass, it doesn't affect it that much, but what like really affected, at least in Santa Cruz SAM, is how the black hole's mass is computed. Because Santa Cruz SAM, like the way that the black hole grow in Santa Cruz SAM is through mergers. So each of these, for example, well, we have like very different merger mass. Let's say, for example, like this one is just a straight line. So there's kind of like no mergers here for this one halo. So I would imagine the black hole mass would be very, very small here, though the stellar mass could be somewhat similar. Though there's still some kind of scattering in the stellar mass that depending on the concentration, as you can see from the mass assembly history alone.
Right.
Yeah.
Thank you.
You want to ask more questions? Yeah. Whatever you're finding.
Right, so I understood the first part of your talk very well, the last part not quite as well. But in the first part, you're kind of moving forward in time, right? If you start with a halo of some mass and concentration, you can predict at the next step
Yes.
what that will be.
Yes.
The full distribution, you can draw from that distribution, do realizations.
Mhm.
So the neural net you've learned represents the distribution of kind of all possible ways for that to develop,
Yes.
which is great. And then when you part of doing the full merger trees, it's almost like you just want the same thing reversed in time, right? You want to say, I end up with something of some mass and concentration. I want to know how I got there.
Hmm.
Right?
Yeah.
It's too bad because the forward in time one in some sense already contains all of that information. If you could just invert that function. I don't know how to do that, but
Yeah.
you know, especially if things didn't depend on redshift or the local density or whatever, which they do, but you can have it conditional on that. If you didn't depend on that, then I mean, each of these sub-halos feeding into the big one is kind of like a prodigious sub-halo of its own. You know, so it just, I mean, you found a solution and it looks like a good solution, but I just feel like that original neural net kind of already contains all of the information. So is there some other approach to this that would be easier and faster?
Yeah, so we actually think about this a lot. But with the previous one, you don't even need to invert it. You can always just go back. You can always train it like backward. Like from, let's say start, you can always
Yeah, you
start
can
from
train it
0 to 10
backwards, yeah.
and you can go to 0 to 0. I think like the reason that we kind of like resort into this is because then, so you can model everything from kind of, so one is like choosing the start redshift and also choosing the mass at the start of redshift might be a little bit tricky. You can kind of like always start everything at like the same mass and kind of like evolve it from there. But sometimes it can create like out of distribution problem in your data. And the second reason why we didn't do that is because let's say you have two frames, like let's say two halos that evolve as a function of time. How do you determine that they're gonna merge? And I think that's like the thing that we was trying to like was thinking about and then decided we will like go with this. But I can see how you can like kind of like do that if you can like model the merger rate accurately. Because let's say that if you look at this, let's say that you look at this tree. Let's say that you have this halo. I'm trying to pick a nice one. Let's say you have this. You have this, and you have this, and you can evolve this halo. But then, like, when did you determine that it's going to become one halos?
Yeah, no, well, I mean, that's why I'm talking about reversing time. If you
Yeah.
could go the other way,
Yeah,
you know, each bit of mass that you want to add at this time, you can run it backwards as if it were the whole thing.
yeah.
And then you basically got that whole diagram, but
You can actually do something very similar to redshift because they also just modeling this, but the way that they determine this split is that if, you know, they say that if, you know, this chunk here is too large, then there has to be a mergers, and then you can like kind of model these mergers. But with the frame way with FLORAH, what we found is that if we try to do that, we actually do have to train another network on, you know, the secondary branch as well, not just the one on the main branch. Because the mass jump from this to this, and the mass jump from like this to this, or like this to this, is like captured by different distribution. And
okay,
just
so
because
there are different distributions.
they're
Because
not
this whole thing
exactly-
looks so self-similar.
Yeah,
right?
I know.
I mean, this chunk looks a lot
Yeah.
like that chunk, and this chunk is a lot like, yeah, I mean, it looks very self-similar. So,
Yeah.
yeah,
I think that's what we're trying to solve as well, because like if everything is so similar, you can just train this and then like you kind of solve everything.
yeah, exactly.
So I think that's where we started doing the mass assembly history first, and then we found that things is not like as self-similar as we wanted
It's
to
not
be.
as, okay,
Yeah.
okay. The universe is more complicated than a simple model can.
Yes.
I have a question, I think this is pertaining to your next slide, because the normalizing flow, yeah, I think this one, the normalizing flow. I think in the last step here, you said something about the dimension changing, which is why it's challenging to use the normalizing flow somehow, I didn't catch what exactly is the workaround?
Yeah. So the workaround is that we only let the flow predict in one halo at the time, right? So you can imagine that you can feed, you know, this entire history, and you can have a flow that is multi-dimensional. You can have a flow that predict two halos at a time. But then what happened when you only have one merger is what happened when this is equal 1, what happened when this is equal 3, for example. Then you need like a 1D flow, or you need like a 3D flow. So we actually did also experiment with just having multiple normalizing flows. So like we have like a 1D flow for a case with one mergers, we have a 2D flow for a case with two mergers, and we train all of them simultaneously. And we found that doing so does not give as good as a result of this model in things like this.
So it's one on each.
Yeah. So it's model like the first halo, give it some kind of like starting token. Kind of like just how to generate a sentence. And from that, it predict the properties of the first halo, and then it takes pretty much the properties of the first halo to predict the properties of the second one, and it takes the first and the second to predict the third. Yeah. But in general, we found that like the number of progenitors is not really high, like it's go from like 1, 2, and 3, but anything beyond that, the effect is very minimal to the entire mass history of the universe and of the emergent trees. So in general, you don't even need to like kind of like use this kind of flow. And that's also a reason why the multi-dimensional flow is kind of working, but not as good.
Any other questions or comments, discussion online? One person? Yeah, ma'am. Okay. Yeah, go ahead.
So for the validation of your model, the first part, it was something, the main progenitor history.
Yeah.
I just wonder, like, have you compared to some very naive baseline model, like just randomly draw a line from the range of the image over redshift distribution and compare with that?
I think we have not, like, I think like most of our comparison was like mostly eyeballing by just like seeing that this distribution match, why, you know, if you
Like,
look at.
imagine you just randomly draw a line from the, like, the tail over different validation of the exam model from that, shaded region, if we go to your previous slide.
Like,
Or even, yeah, something like that.
Yeah.
Or, you have a image over the redshift from in your place.
wait, this like this. This is always correct, right? Yeah.
You just randomly draw lines from the distribution and you average over that to complete over that. I just wonder, like, if you just compare with those like naive baseline models, but that, is there any metric to show that the current predicted virtual history is better?
Yeah, so mostly the method that you described has been done, and these are, for example, you can just like model and, you know, and by automatically you can kind of like fit some kind of exponential function as a function of redshift, and you can like kind of still condition the parameters of that function with, you know, the initial mass and the redshift, and you can get like pretty decent results as well. But the problem with those methods is that like your mass, you know, your DMDZ is always going to be the gradient of that lines. So in a sense, you cannot capture chunk, right? Say, for example, if you look at, and I'll show you another plot too. If you look at this, and maybe a little bit hard to see, but you see some jump here, right? Some like very abrupt jump, which is kind of like indication of mergers. Even though in the mass assembly history of the first model, it's not very obvious because there's no like explicit mergers. But you can do see kind of like this jump. And one thing that I do have on the extra slide, sorry, this Twitter is reverse. Is that one thing that like those methods, like if you just draw a line, you can't really capture it, you cannot capture this entire distribution, where you have, this is the log of m progenitor divided by m descendant. And like this is for different redshift slides, each row with different redshift slides. Each column is different mass, like mass length. And like here, you can kind of see that you can capture the entire distribution here. And this distribution here does change, like does change a bit. And there's a lot of like jump, right? There's a lot of mergers here, which you can see by indicated by this very large factor here. And with, you know, just drawing line, you can't really fit that.
Thank you.
Anyone else? Any other questions, discussion? Okay, well, let's thank Tree again. We can have lunch and continue discussion. We have new sandwiches. Be sure we leave some